I had a very interesting day talking to people here about their science and catching up on some of the latest things that are going on here at Carnegie Mellon. And some of it overlaps with some of the things that I talk about, that I'll be talking about. So when you hear them talk, perhaps some of the things that I mentioned will put a little bit in perspective. So I've chosen this, well, it's a fairly elaborate title. I'm a condensed matter physicist, a theorist, and sometimes called solid-state physics. And my job is to predict the existence and properties of new materials and to try to explain what the experimentalists measure. So they'll bring these wonderful experimental data to me, and I try to make sense of it. Or I can say, if you do this, this will happen. So it's really a very wonderful life to be in a position to do this. And mainly, I do it with the aid of excellent graduate students. And through models that I work on, mostly pencil and paper, and the great proficiency of this next generation with computers, we're able to achieve these aims. One of the most important concepts in all of science is that macroscopic matter is made of atoms. The concept of an atom goes back to the Greeks, but the actual picture of what an atom looked like developed over time. In particular, Thomson discovered the electron, and the electron was negative. So he knew it had to come out of a positive region because atoms are neutral, and he pictured an atom as a pudding of positive nature, and these plums in the puddings were the electrons that he pulled out. It's not such a bad model. It's not our current model, but it's not so bad for explaining some of the properties of, let's say, metals. But then around Newton's time, they knew that atoms would bind together and form solids, so they pictured atoms as having hooks. And so the idea is, how do you put atoms together so that they'll form solids? And the way we do it nowadays is through the quantum theory. So I'm going to tell you a little bit about what a quantum atom looks like, or try to give you an impression of it, and then talk about how you put this together. Now, as Fred mentioned, in 2005, I was president of the American Physical Society, and it happened to be the year of physics worldwide. And we were celebrating the 100th anniversary of Einstein's miraculous year in 1905, when he did incredibly wonderful things, working in a patent office, and many of you know the stories. And he was determined to establish the existence of atoms. At that point, people were still arguing about whether atoms existed. And he actually worked on the determination of molecular dimensions. He also worked on Brownian motion, which is if you suspend particles in the air, they'll be bumped around by molecules, so it shows that molecules actually exist, atoms actually exist. And then relativity, and finally, which you know about, and I'll say something more about it, and the photoelectric effect. This effect is you shine light on a metal surface and electrons pop out. Turned out to be an extremely important experiment, and his theory was very important because it showed that the light that came in could behave as a wave, but it could also behave as a particle. So the photons, which are associated with the concept of light, went in and bumped the electrons out of the material, came out. And in fact, this is the work that he received the Nobel Prize for. But it wasn't always so easy for Einstein. He had several attempts in trying to get his thesis subject approved. For example, he went to Professor Dr. Weber around 1900, and he proposed that we should measure the speed of light in different directions. And later, this experiment was done by Michelson, and this was the first Nobel Prize for an American. But Professor Weber rejected that as an idea for a thesis. So I hope there's students out there that can identify with this kind of thing. But he went back and he proposed to work on the effect of how heat changes the electrical conductivity of solids and the conductance of solids. And this is a very important problem, particularly now in electronics. And unfortunately, Weber didn't see the use of this. So he tried again, and he took the other approach with heat, said, let's look at how heat flows through solids. And he developed a theory, and he wanted to use that for his thesis. But he wrote it on the wrong kind of paper. Weber was angry by this point. Nobody really felt Einstein was an Einstein. And so he said no. So he went to Professor Dr. Kleiner. And he wanted to talk about and work on a very important problem, which is you take gases and you have isolated atoms, and you bring them closer and closer together so the atoms start interacting with one another, and they form a liquid, and then you squeeze more and they become a solid. So you wanted to work on interatomic forces and intermolecular forces, and this is a fundamental problem. And Kleiner must have talked to Weber and didn't work. And then this was a big mistake by Professor Dr. Kleiner, because Einstein proposed to him that he wanted to work on the electrodynamics of moving bodies. This is my cereal bowl, which my wife gave me. A is for whatever, apple, B is for ball, C is for car, D is for dog, and E equals mc squared. And that could have been the Kleiner-Einstein equation. But Kleiner didn't see the light, and he rejected it. Finally, he did some theoretical work to explain properties of sugar molecules and wrote this up as a dissertation because it gave people a chance to measure the sizes of molecules and to establish that atoms really existed. And he included Kleiner and Burckhardt. They said it was too short, 17 pages. He added one sentence, and that was his thesis. Now, Einstein went on, of course, to do miraculous things, but a lot of these miraculous things were based on the things that he thought about as a student. And during that wonderful year of 1905, he successfully worked on this. Now, the big revolution in physics, in this part of physics, came with the development of quantum mechanics. And that happened in the 1920s. And by 1929, Dirac proposed the following challenge. He said, we've given you the underlying physical laws necessary for a large part of physics and all of chemistry. And he said, now what you have to do is take these complicated equations and solve them. And basically, my talk today is a report on what's happened in the past 83 years and how the quantum mechanical theory can be reduced to a form where you can actually solve things. So the difficulty is that for a quantum atom, instead of having these atoms with hooks or plums and puddings, you have a nucleus, which was discovered by Rutherford, and then the electrons that are important for building solids are around the outside, and they're fuzzy. And in fact, you can't tell exactly where they are, but you can tell with great precision the probability of finding electron densities at certain points. So the theory is based on looking at the probability density for electrons. And the question is, how do you take a system like that, put those things together, and make solids out of them? And there is a philosophical aspect to this that I thought I'd bring up because many physicists are talking about this, although usually when you talk about philosophy of science, physicists sort of leave the room saying that the philosophers don't know what's going on. But this argument has been going on, and it's interesting to look at it in the light of this field of condensed matter physics. So I want to put these atoms together, and I want to get a mental picture of what a solid is like. And there's two fundamental models that have developed over the years. One is that the atoms just interact with each other. So I should start with the atoms and see how they're changed. And another one is called the elementary excitation model. And I'll tell you what that is in a moment. In the interacting atoms model, you say a solid is a collection of strongly interacting atoms. And from the philosopher's point of view, this is called reductionism. If I say I know the particles are these nuclei and electrons, I know that they interact through electromagnetic interactions because the other interactions like gravity and so forth are too weak on this level. This is the appropriate system. And so I should be able to start from atoms and tell everything. And so this is one approach. And as Fred mentioned, the pseudopotential. What the pseudopotential does is if I line up my atoms in some specific order, then the nuclei will, which is the dark part at the center. I think this has a laser on it. But, anyway. Is it shining? Okay. The nucleus is this dark part. It doesn't really make much difference when you form a solid for the nucleus. It doesn't change very much. So there are core electrons. For example, if this is silicon, it has 10 electrons that sit very close to the core, and they don't change very much. And then those extra 4 electrons form this fuzzy soup that make up the properties of the solid. So in fact, if I can calculate the energy of this whole thing and then move these atoms around and look for the lowest energy, nature always wants the lowest energy, I can tell you the structure of silicon knowing only the number of electrons and how the electrons interact with the core, and that's the pseudopotential. And we can build the pseudopotential for any atom in the periodic table. When you teach solid-state physics, you talk about silicon and diamond. And so this is an old view graph. And you say that each silicon atom is surrounded by 4 other silicon atoms. And this is the same thing whether if this were carbon, then that would be diamond. It's a very strong bond. So this is a ball and stick model. These are those atoms, and those are the sticks. And the sticks are the valence electrons. Well, now you can go in theoretically and calculate where the electrons are. And as I mentioned, it's a probability. So the probability density is that the electrons will pile up halfway between the 2 silicon atoms and form the bond. And this is an honest theoretical piece of work because it came before the experiment, and the experiment came afterward, and you can see the similarities between the covalent bonds. So this is one of the strongest bonds in nature. It's a covalent bond. And although this is for silicon, it would look similar for other materials. So with this method, using this approach, for a broad class of solids and clusters and molecules and the rest, we can tell you where the electrons are. We can actually predict crystal structures because we can actually tell you how far apart the atoms will be by choosing the lowest energy. And we can get this whole list. This is the commercial properties, many properties. So at one point, we were labeled quantum alchemists. In other words, this is a picture drawn by Roz Chast, who usually does cartoons. For those of you who read The New Yorker, you've seen her cartoons. And she pictured the quantum alchemist as having all these kinds of things. But actually, all you need is graduate students and computers. And this was at a time when we were looking at the possibility of making things that are harder than diamond. Now, from the philosophical point of view, there's another approach. And it's actually a practical approach. And that is, if I claim that all I know about the solid, this is a picture of a solid, is what I measure. And if I probe the solid, I'll measure different things. And then what goes on in the black box is something that I can think of in another way. So let me give you an example. If I shine light on a solid and I want to know how the solid's reacting, I measure the reflectivity. And when I measure the reflectivity, if I can explain that reflectivity in terms of fictitious particles, let's say I didn't know that it was made of electrons and so forth, Then I have a theory. Now you may say that that's cheating, but I'll take you further along here. Let's say I put temperature in. I measure the heat capacity, which is how the solid heats up how much energy goes in when I raise the temperature. Or I can put on a magnetic field or whatever. So the idea is this picture has a probe, and you measure the response. And the idea is that particles that explain the properties emerge. And this is emergence theory. So the philosopher would say that the earlier model, where I put atoms together, is called the reductionist model. And the emergent model is like a model that biologists use. Where does life come from? Well, it emerges. You put all this stuff together, and all of a sudden it says hello. And you have consciousness and life. Well, here, for example, if we talk about hitting the solid with a hammer, the atoms are going to vibrate. And they'll produce sound waves. And you can think of those sound waves as particles called phonons. And those phonons become real to you because you can explain the properties, all the responses, in terms of these phonons. An excellent example is the concept of a hole. If you have 10 to the 23rd electrons per cubic centimeter, that's 10, all the way out, in a semiconductor, and you take one out, you shine light and take one out, it's a lot more convenient to talk about the absence of that electron as a positive hole. Electrons are negative. And think of how the hole moves than to look at how all the 10 to the 21st. Now, I can't throw a hole across the room, whereas in principle you can throw an electron across the room. But engineers in Silicon Valley spend their whole lives on holes, these fictitious particles. So the question is, what's real? Is that hole real? Is it a way of describing nature? And what do we know? Well, back around the turn of the century, there was a lot going on in discussions of this kind. And in particular, Henri Bergson talked to Einstein a lot about these things. Bergson talked to Einstein a great deal because he didn't believe in the theory of relativity. And eventually, Einstein convinced him that it was true. Bergson had made he was a French mathematician and made some important contributions to mathematics. And then once he got into science, he started thinking about science philosophy. And he said, everything we sense are images. It's through our senses. So depending on how you describe it, you have to describe in terms of images. And so he is sort of one of the fathers of emergence. And this is being debated. By the way, he went on to get a Nobel Prize in literature. So he was a very talented person who worked in many areas. And Einstein, when he wrote his Nobel Prize paper in 1905 on the photoelectric effect, it was called Considering the Generation and Transformation of Light from a Heuristic Point of View. He really meant that this was a model, and it was very much emergent properties. He didn't go through all the various details, and he was more interested in the concept that light could behave as a particle or a wave, even though he couldn't picture it. So in a sense, it was an emergent point of view. And he went back and forth between emergence and reductionism through his life. I thought I'd mention it because these questions are being discussed by physicists nowadays on what's the most appropriate thing to do. And in my field, it turns out you need both. So I'll just mention, I won't go into detail on photovoltaics, even though people are working on that here, but Einstein's theory of photoemission, looking at how electrons pop out of surfaces, is very useful for calculating how to make better photoelectrics. Our problem is that this is the solar spectrum, and the silicon is the most used material for photovoltaics. So you want silicon to absorb a lot of sunlight in this energy range. You see it doesn't. And once it absorbs the light, then that turns into electrons and holes, and this gives you a current. So if you can modify silicon so that it absorbs light in that range, you do much better. And using these techniques, we are now able to do that. And so it's very helpful from a practical point of view. Okay, nanoscience. I was at the Physical Society, American Physical Society meeting in Boston last week, and the most discussed topics were nanoscience and superconductivity. So I thought I'd tell you a little bit about it. Nanoscience just means that we're studying things on the nanometer scale, 10 to the minus ninth of a meter. And this is a scale which is of interest to physicists, to chemists, to material scientists, biologists, engineers, computer scientists, because this is a scale where you make devices. This is a scale where the biologists are working for many of the things that are important for biology. And this is roughly the scale of the nanotube. And there's atoms, and DNA is here, and all the rest. And so that has brought us together. It's actually broken down walls between departments. Years ago, the Department of Energy would give us extra money if we would work with chemists. And we said we would, but we didn't. We took the money. Now we work with chemists and we work with biologists because molecular motors and nanomotors are similar. And the latest rage is graphene. This was a Nobel Prize for 2011. If you took your pencil lead and looked at it closely, you'd find that it's a series of layers. A series of layers that look like this. This is an actual picture using an electron microscope. So there are hexagons. There's an atom here, an atom here, an atom here, an atom. So these are carbon atoms, but instead of having four neighbors like it does in diamond, like I showed you before, carbon has the unusual property that it can also have three neighbors and be a layered material. And that's why we're alive, because carbon can form these multiple bonds, silicon can't. And it can form these multiple bonds and make organic compounds. And so it forms these layers, and in your pencil, when you write, these layers come off, and that's what the writing is. So these very, very strongly bonded layers are connected very weakly to each other. There's one stack on top of another, and they rub off from one another. And so what happened was people wanted to work just on the layers. They didn't know how to peel it off. And two researchers, I'll give you their names later, took Scotch tape, put it on top of graphite, which is pencil lead, and peeled it off and got individual layers. And then very soon after got the Nobel Prize. So this is what a picture of what a layer of graphene would look like, all these hexagons. And if you cut out the appropriate geometry, you can bend them around and make a Buckyball, which is a 60-atom molecule. Or if you just roll up a piece of, and nature does this for you, of graphene, you make a carbon nanotube. And you can look at graphene ribbons, which is slices of these. People can cut these out, and single layer, bilayer, and so forth. And this is the current rage. So I'll give you an example of a nanotube calculation which has been shown to be correct. If you take a sheet of graphene and you bend you go around 8 layers, 8 hexagons, and don't move it up or down, just come around like that, that will be a semiconductor. And if you go around 7 times and push up by one hexagon, that'll be a metal. That's how versatile these materials are. And you can put them together so that you have a metal semiconductor interface. If instead of having 6 and 6, you have same number of atoms, but 5 and 7. And this forms something called a Schottky barrier, which is an electronic device that you can build radios and so forth out of. So on a very small scale, you can create devices and do all kinds of things. Now, there are wild things that people want to do with nanotubes, and I'll tell you about one. You want to make a space elevator. The idea in the old days was to try to build a tower to the moon, but they realized the materials weren't strong enough. And then Sir Arthur Clarke, the science fiction writer, said that you could get satellites going around the Earth, and if you put them in the right orbit, they'll stay right over one place. In other words, as the Earth rotates, it will stay there, so you can put one on above Carnegie Mellon. Then all you have to do is build a cable, and you can take things up and bring things down and all the rest. And so there is a project, primarily at Los Alamos, to make a space elevator using carbon nanotubes and trying to see whether or not they can take things up and down. And they want to have one going around Mars and put things down and up. If you actually calculate the strength of the carbon nanotube, which is about the strongest material in the world if you pull it this way, you find it's about a tenth of the, it has a tenth of the strength that you need to even have something that long. But they're trying to weave these things and do all kinds of things. So I don't know about this project, but I'll show you a project that does work. And it's very interesting. The carbon nanotubes actually sometimes form as a single cylinder, but they often form like these Russian dolls, a cylinder within a cylinder within a cylinder, concentric cylinders. And the experimentalists can reach in and pull out one of the cylinders and let it pop back in and so forth. Now the cylinders themselves, because the bonds are very strong, they retain their identity, they're very good. But between the cylinders, as I said in graphite, is very weak. So this has almost no friction. So it's like a frictionless bearing. And so the idea is to make a motor out of it. So first I'll show you a schematic of how you make a motor, and then I'll show you a real one. You take a carbon nanotube. In this case, it's a multi-walled tube. It's got two tubes, one inside the other. And you put it down on the surface, and the yellow is gold. And you configure it so it has a little piece of gold on it. And then these are just electrodes. And if you go inside and look at what's happening inside the tube, you'll see that there's an outer tube, and then there's an inner tube. And these tubes like to form in, as bitubes, having two tubes. And so you pulse this piece of gold, and make the thing turn. And you break these bonds. So the outer tube moves around separately from the inner tube. And if you put on electrical contacts by changing the positive, negatives, you've actually made a motor. And this is what a real one looks like. If you, the tube is going up the center. This was the first one made some years ago. They now make them by the hundreds. And so there's a tube going down there. This is a piece of gold, and it goes around. And they're applying it in various ways. So this, to give you an idea of the scale, this little motor could fit on the back of a virus. It's that small. And they can engineer it, and they can make them even smaller nowadays. New direction on nanotubes that's taking up much of my time and other people is a boron nitride nanotube. Instead of having all carbon atoms here, you take replace one by boron, another one by nitrogen. And this is a very, very strong tube. And it's a semiconductor, but you can dope it. And when you have these tubes and you dope it, the electrons go right down the center of the tube. So you can build a pipe for electrons. And they've used it for flat panel displays and for many applications. I'll show you some applications in a moment. But one of the things that's been a lot of fun, and I'll tell you why it's important a little bit later, is that you can get these C60 Buckyballs inside the center of the tube. Now this is a multi-walled tube. It's probably got about 6 or 8 walls. So that's why you're seeing a bunch of lines, because you're seeing cross-section. And these are C60 molecules lined up. And depending on the diameter of the hole, you can get different configurations. So this is schematic. For example, if the buckyball or these ball bearings are the same size as the tube, then they line up like this. If it's a little bit bigger, they start doing this. And the mathematicians have worked out all the different structures you can get. So these are structures that are not in nature, but you can build them and you can make them do all kinds of things. Art precedes science here. This is Man Ray, the famous photographer, and I actually saw the actual piece that he made. This was back in the 30s in Seoul at the museum in Seoul. And as you can see, he anticipated this. So science is sometimes behind art. Okay, I'm just going to mention that we're expecting a lot from these boron nitride tubes. And the only problem is how to make a lot of them. And there's been some new techniques so that they come out like this. The nice thing is they're extremely strong mechanically. And you can make fibers. That's a glove, so that's the size of a hand. You can make yarns and textiles. They can't get dirty. And because it's white, you can actually dye them. Carbon nanotubes are black. And they're using them for medical therapy because boron absorbs neutrons and gets hot. So if you put them in the body and get them to a place where there's a tumor, people have destroyed tumors using these tubes. They're bio-friendly in that we haven't found any reports of them causing damage, whereas you do have damage with carbon nanotubes. And they're using them for storing hydrogen and lithium, so they want to use them for batteries and all the rest. So these are some practical aspects of these tubes. And I'm happy to report that we were able to predict the existence of the tubes just using this quantum alchemy approach. And my colleague Alex Zettel at Berkeley was able to make them. So it was Andrei Geim and Kostyav Novoselov who won the Nobel Prize in 2010. But this table that they made up was in 2011, and people keep showing it because they're trying to explain why graphene is so exciting and why so many people are working on it. Well, it's the thinnest imaginable material because it's 1 atom thick, has a large surface area. It's the strongest material ever measured. This is theoretically because you can't really grab graphene and pull it, but it's got to be the strongest. It's stiff, it's stretchable, it does all these things. So I'm going to just show you one of the reasons why graphene is exciting. And I'll just give you a quick example, but I won't go into details. If you take an ordinary electron and ask what its energy is as you increase its momentum, the energy goes as the momentum squared. And the electrons in a metal, the energy goes, this could be momentum K, go as a square of the energy. And then you fill up all the electrons to something called the Fermi level, and then it's empty above, and you excite electrons from here to here. In a semiconductor is also quadratic. It goes as the momentum squared. And there's a gap, and you take electrons from here and you put in here, and this is the gap that silicon has that gives you the photoelectric effect. But for graphite or graphene, there is no gap. It's zero. And the energy is linear in the momentum. And so people have gone back. They said the physics is totally different. But Dirac had an equation, a relativistic equation for the energy as a function of the momentum and the mass. So for example, if you had no momentum, then E squared would be m squared c to the fourth, so E equals mc squared. But once you put momentum in, for a massless particle, E goes as pc, so it goes linearly. And this does an amazing amount of changes things considerably. Of course, now it's not the velocity of light because this is in a solid, and it's the velocity of light over about 300. So it's this funny property that allows you to do strange things. And I'm just going to tell you two strange things, but I won't explain it all. If you take a piece of graphite and you draw lines on it, and it's possible to draw lines perpendicular, and then you shine electrons, no matter what angle they come in, they go straight. they don't go along the lines, but perpendicular to the lines, they go straight. So you can take a graphene sheet and columnate electrons and make, let's say, flat panel displays and all the rest. Another strange thing, because of these special properties of graphene, is if you cut a ribbon of it, so these are just carbon atoms, and then the electrons have spin. And because of the nature of graphene, at one end, the spins will all line up, at the other end, they'll line up down. And if usually you change the direction of a spin with a magnetic field, but here, with an electric field, you can get all the electrons lined straight up or all the electrons lined straight down. So you can polarize electrons, and that's a very important aspect. So I just wanted to say that graphene is different, and there's a lot of reasons for studying it. Okay, my last topic is superconductivity. It was discovered in 1911, so last year was the 100th year anniversary, and we celebrated all around the world. And it was discovered by Kamerlingh Onnes in Leiden. And there are many stories about whether he was around when it was discovered, because his students were there in the lab and then tried to convince him that it was there. But there are many versions of this, and it's discussed in physics today. But basically, he had liquefied helium, which allows you to go to temperatures down to around 4 degrees Kelvin. This is on the Kelvin scale, very, very cold. And they measured the resistance of mercury, and instead of it coming back to a constant, it went to zero, really zero. And even in those days, they could measure this to 10 to the minus 5 ohms and found that it was zero. So no resistance. It flows without resistance. That means, and this experiment was done soon after, that if you took a piece of metal, this is just a metal wire, and you got a supercurrent going in it, and you kept it cold, that current would continue forever. If you calculate how long forever is, it's longer than the age of the universe before this thing would decay. So, because electrons making a current going around in a circle produce a magnetic field, you could carry a magnetic field from one place to another. And I forget who the first person was to take a ring of this from Leiden and took it over to England. But the problem is you have to keep it cold, and it had to be liquid helium. And Onnes attended this very famous Solvay conference in 1911 that had some of the greatest physicists of the time. There's Marie Curie, easy to pick out because there's only one woman. Here is Max Planck, who started quantum mechanics. Sommerfeld, who was one of the leaders in my field. Rutherford, who discovered the nucleus. And that's Kamerlingh Onnes. And he's a very happy man because this was in the fall of 1911. And he discovered superconductivity in the spring of 1911. And he's standing next to Einstein. And it's clear that he told Einstein about superconductivity. And it's clear that Einstein said, because he said it in later years, no one would ever figure it out, something like that. Because he said it's a complicated cooperation between molecules and how are you going to do it and all the rest. And he actually wrote some papers. Well, it took 46 years to get a theory of superconductivity for the material that Onnes discovered and for materials like that, and I'll tell you about that. And we have a class of materials today that are not understood. So what happened after Onnes was, here's the transition temperature. In the Kelvin scale, if dry ice is about 200, so it's way, way up there. So this is where mercury was discovered, and this is helium. And it climbed at 1/3 of a degree per year, the highest temperature, and sort of sat around here in this range of about 20 degrees. And then in 1986, 87, the superconducting copper oxides were discovered, and they're much, much higher, in fact, above liquid air temperatures. So that, in fact, you could take, and We all went off to high schools to do this. This is a picture of a train, and it's sitting on the so-called 1,2,3 material, yttrium, barium, copper oxide. I'm sorry, these are magnets on the bottom of the train. And then there's this high temperature superconductor. You pour nitrogen on, and then the train levitates. And there are real trains in various places that people have experimented with that can levitate. But the idea is that you have to keep them cold. Well, the problem is that we understand the theory of these materials, which I'm going to call class 1 materials. But these materials, class 2, although many people have theories, there's no consensus. So the Solvay people actually got a bunch of us theoreticians together in 2008 to try to reproduce in the same building, the Metropole Hotel and all the rest, to solve this problem of superconductivity. And of course, we were not able to. My wife points out that all week, everybody was dressed in their usual terrible clothes, but when it came time for the picture, they all appeared like this, and everybody wanted to stand where Einstein stood. But it turned out they were very upset when they found out it was a different room. And so there was a cartoon in the New Yorker that happened to come out just then. It says, can we start over like 1987? This is a theorist talking to a psychiatrist. Because till today, we don't really have a good theory for those class 2 superconductors. But one thing we know, and that is that like the class 1 superconductors, and that theory was explained by Bardeen, Cooper, and Schrieffer in 1957, we know that the electrons are paired. So the question is, why, if you pair electrons, will the electrons go through a wire and not lose energy? Why is that superconducting? And to explain this, you think about going to a dance. And you and your partner are going to dance about 15 feet apart from each other, long distance. So there'll be other couples between you and all the rest, but you know who your partner is. And whenever you move forward, your partner moves forward. You move back, your partner moves back. I mean, that's the agreement. And when you bump off something, even though your partner doesn't have something to bump off, your partner bumps off the opposite way. So as these electrons move, no matter what happens to them, the partner, if one loses momentum, the partner picks it up. And so all you need to create superconductivity from this Bardeen-Cooper-Schrieffer theory is for the electrons to match up, to attract each other. And electrons are negatives, so they repel each other. But it turns out, in the Bardeen-Cooper-Schrieffer theory, you can activate the lattice, those phonons I talked about. And one electron will pull the lattice in such a way that when the second electron comes by, it tries to follow it, and it looks like the electrons are attracted to each other. Or as we used to explain it in the 1960s, if you put 2 ball bearings on a waterbed, they'll make depressions, and they'll come together. So one of the ball bearings will see the depression of the other one and fall in. So they polarize the lattice. So that's the theory. And if you divide all of superconductors into these 2 classes, the first one, even metal, conventional metals, organics, magnesium diboride, which is about a 40-degree superconductor, highest in this class, they all fall into this category, and we know what binds them. Here, we don't really understand them. That's class 2. So the bottom line is every single experiment that's ever been done that I know about on class 1 superconductors has been explained. And there's no consensus on the mechanism for class 2. Now, so if you understand class 1, can you explain it from first principles or even predict them? And I'm happy to say that we're able to predict many of the class 1s, several of the class 1 superconductors. And we just have to know essentially one thing. This is a formula for the temperature when, for a superconducting transition. And the important thing to realize is that this lambda is the strength of the electrons coupling to the lattice. That's what's forming the pairs. This is the repulsive Coulomb interaction. You can forget about all the others. And this is the frequency that the lattice vibrates. So if I know the frequency the lattice vibrates and I know how strongly the electron couples to the lattice, I can give you the transition temperature because we can calculate this. And in fact, it gets even simpler. If lambda is really strong, if you want to make a really high TC superconductor, let's say room temperature, which is what the holy grail for this field, everyone is trying to get the higher temperatures, then it really just, all you need to know is the strength, electron phonon strength, and the phonon frequency. And it's just the square root of that. So let me quickly tell you that in the early days, we could predict that some materials would be superconducting using semi-empirical approaches. But now, in fact, we can start along the lines of the beginning of the lecture with this quantum alchemy. We could predict that silicon, even under high pressure, will become a metal. We can predict its structure. We can predict everything about it, its existence, its stability, its lattice constants, and even its superconductivity. And the only thing you have to put in is the atomic number and the atomic mass of silicon and these estimates. And so these new silicon materials, which didn't exist before they were predicted theoretically, were found, and they're superconducting. But they're not really very high temperatures. So the question is, how can you get, since you understand class 1, can you get the higher transition temperatures? And this will be the last subject. So we want large lambdas. We want the electrons to couple strongly to the lattice. We don't want it too large because it'll distort the lattice, will go unstable, and you'll lose the effect. So we avoid stabilities by going to cage structures where the system is held together by something else. I'm going back to this. For example, these boron nitride nanotubes. We've put in the C60s, and now they're putting potassium in, and the potassium is interacting with the C60s, trying to get a higher transition temperature. So I'll just give you the bottom line on the latest work on trying to get the high temperature superconductors. I mentioned that the transition temperature goes like the square root of this lambda parameter times the phonons. It turns out that that's the same as an electronic spring constant that we can calculate that's very strong for strongly bonded materials divided by the mass of the atom. Square root of this gives you the transition temperature. So we're looking for things that have strong bonds and light masses. And that brings us all the way back to diamond. But diamond is an insulator. So you have to get carriers in, and people are doping diamond. And the first discoveries were in Russia, and they got it to 4 degrees. Now they're up to 11 degrees. And there's a big effort trying to get higher. And we can show that if you look at the transition temperature, this is an old picture, but it shows that the transition temperature as a function of lambda keeps going up. The early theory said it would stop. But we know that this is correct. It goes like the square root of lambda. And some of the predictions give superconductivity in diamond could go up even to room temperature. But there's a problem when you make predictions, as Yogi Berra said. Predicting is difficult, especially about the future. And up to this point, the highest temperature superconductors are these copper oxides. And I can't tell you how to make them higher temperature because we don't understand them. And now we have new systems that are getting up to that range with iron in it. And they are also in the class 2 region. So we only can explain the class 1. So to sum up, our standard model is interacting atoms and elementary excitations. We need to use both in understanding solids. And nowadays, theorists can explain and even predict ground state or excited state properties of many condensed matter systems. But all decisions in physics are made by experiment. But maybe with these new techniques, we'll be able to predict new states of matter and maybe get a jump on the experimentalists. And the question that comes up in my field, often the work is very basic, and it's as basic as it is in other areas of physics, but sometimes it's applied because we work with semiconductors and all the rest. And so when a student asks if light is a particle or a wave, you give the same answer for that as you say, should I do basic or applied science? The correct answer is yes. And because they feed on each other, and sometimes the applications push you in a new direction for basic science and vice versa. And the question of basic science and when it's useful. When William Gladstone was the English finance minister, he later became the Prime Minister of England, he said to Michael Faraday, who was an extraordinary experimentalist and did the early work on electricity, well, what is the practical use of electricity? And Faraday said, I don't know, but someday you may tax it. Our students learn about Maxwell. Maxwell is a theorist, and he wrote down with his Maxwell equations much of what Faraday did. And so they learn about Maxwell, they don't learn about Faraday so much, but Faraday made the essential contributions, and of course Maxwell did an incredible amount of work. But the relationship between experimentalists and theorists is complicated, and I work with a lot of experimentalists, and that's why I like this cartoon, which says, to be honest, I would never have invented the wheel if it were not for Erg's groundbreaking theoretical work with the circle. But I think the best quote, so that you can put my talk in the proper context, is from our friend Albert Einstein again, when he said the most valuable tool of the theoretical physicist is his wastebasket. Thank you very much.
Okay, I think we still have a few minutes for questions, if there are. Some microphones around the room. Any questions? Yeah, Randy Deason.
Comparing graphene and silicon. So some people would argue graphene electronics could sort of replace silicon technology. Other people might argue for, other special applications. What's your view?
I think that over the years, no matter what anybody did, silicon won. You remember at IBM, they were going to use superconductors for computers using the Josephson effect. And I remember my colleague at Berkeley, John Clark, who works on this, and he came to me and he said, silicon's passe, it's all this. And that the machinery for silicon is amazing. There's so much invested in equipment and all the rest. So for general applications, it looks like we're going to have silicon for a while. Having said that, some of these new devices that people are making with graphene are amazing. There are people who are using almost a single atom for a transistor. And the fact that graphene has such high mobility and it's so fast and all the rest, I think it will come up at the beginning as a material for special needs. Just like for photovoltaics, you can get very efficient photovoltaics, and these go into projects that NASA is involved with, whereas the usual photovoltaic on your calculator is an amorphous material or something like that. So I'm not really answering your question, but I think in the short term it's going to be silicon for a while. And they keep saying it's getting, these problems, Moore's law is not going to keep working. Well, if it's almost Moore's law, it's not so bad because we've got all the machinery, and Apple keeps making announcements on new things. So it's going to be that for a while. But in the long term, perhaps these other approaches. The nanotubes also look like they may be useful for some of these applications. In particular, if you take a nanotube and functionalize it, which means you put molecules on the outside, it can detect better than the nose of a dog molecules that come in on it. So for example, on a regular watch battery, you can build a detector made out of a nanotube, put it on the wall, and it'll tell you how much carbon dioxide is in this room. It'll tell you all kinds of things very simply, and very important for medical applications with very little power. So applications that we hadn't thought of, like we didn't really know we needed an iPad, but applications that we haven't thought of, these things, graphene or carbon nanotubes or boron nitride nanotubes and all these new materials might be work for us. You see, I talked around the question. So the bottom line is I don't know which is going to be the best.
Yes, those who have been physical chemists, organic chemists interested in boron and nitrogen, have always thought that the vacant orbital functions of boron 2p and silicon 3d were important. Do you utilize any of these?
No.
I thought so.
No, in fact, sometimes, great respect for chemistry. I didn't understand it until I was 50 years old. But sometimes you get the wrong answers with some of these orbital things. Back when we were doing these things. Nowadays, everybody gets the right answer from the point of view of starting with orbital theory and quantum chemistry. But for example, if you take gallium arsenide, and if you asked most chemists, they would say the bonding orbitals and the valence band are bonding, conduction band anti-bonding. They would be out someplace. But we know that the conduction band states are sitting right on the arsenic atom because we can calculate. We start off totally unprejudiced, plain waves. They're just basically constant density everywhere. And we turn the thing on and say, now find what's going to happen. Whereas in the approaches starting with orbitals, you start off with a prejudice. It's much better if you're close because it's much cheaper and you don't have to go through all the shenanigans we go through in terms of there's shenanigans, but there's nothing you put in. I mean, there's no input parameters. But so the answer is we don't use that. But they're wonderful methods, and nowadays both things work.
One more question, what then?
You showed this E versus momentum as a linear, is a direct ratio. The most simple ratio I understand are non-relativistics. So do you think we should go beyond non-relativistics?
This has nothing to do with relativity. It was it's basically an accident of that if you put something like a carbon atom in a sp2 orbital and you make a graphene or graphite, then the calculations come out like this. And it was done in the early 1940s, calculation at the McGill University by a theoretical physicist who certainly would have shared the Nobel Prize with these people if he had lived, because he had that. I knew about it as a graduate student, so what? Whereas we were talking about this afternoon about Exxon Laboratory when someone took me in and showed me carbon clusters and said, look, there's a lot of them at 60. And I said, oh yeah, why are they all at 60? While I was doing that, someone said, let's go to lunch. And there was the Buckyball. I mean, these things happen. So here, this man actually predicted that you would have a spectrum that's linear. And it's not relativistic, it just looks the same thing, just taking the same. So now people in particle physics are applying their methods to graphene because the dispersion relation is the same, but the physics is totally different. This is not a relativistic calculation, non-relativistic.
Okay, very good. So congratulations again.
Thank you.
Thanks for a great talk.